Hello, good morning. Assalamualaikum. I'm a physics student from University of General Sudirman, Indonesia. In this video, I will explain to you how we look the Heisenberg uncertainty relation in the relativistic domain. And you know that the Heisenberg uncertainty relation have been written for a long time as delta p times delta x is approximately e to the power 2, or written as a delta E times delta T is approximately e to the power 2. And my question to you is Heisenberg uncertainty relation in the previous formula is true for relativistic, or it means that it is consistent with a Lorentz transformation, or it is just consistent with a Galileo transformation. And you know that from Lorentz transformation, we can find that there are phenomena like length contraction, time dilation, and increasing the rest mass. And when we see another side, this is a quantum phenomena, we can find that there are uncertainty of the energy, momentum, a position, and also time because of Heisenberg uncertainty principle. And my idea is simple. I just want to see the phenomena is caused by the Lorentz transformation in the context of the Heisenberg uncertainty relation, and how we reconcile both quantum and relativistic phenomena, so that from this reconciliation we can get the understanding that will Heisenberg uncertainty relations be modified when we bring this relation in the relativistic domain, or it's still consistent with the formula like the delta p times delta x is approximately its power 2, or a delta E times delta T is approximately its power 2. We will have now that the Heisenberg uncertainty relations will have a modified or not through my simple analysis using my simple calculus. Okay, for the first time, I will explain that the energy of the relativistic quantum particle is okay. This is the relation of the energy and momentum for relativistic particle. This is the common formula, and then we can rewrite this formula to the particle picture in the term of the mass. This is the energy formula above is rewrite in the term of the mass, and then we can also rewrite this relation in the wave picture so that we can get this formula is expressed in terms of a frequency and wave number, so we can resolve between the particle picture and the wave picture, and both of them are the same described about the quantum relativistic phenomena. We remember that the quantum particle have the characteristic of the Broglie wave. So the wave characteristic of the quantum particle is described by the wave picture. Okay, we can focus a problem to the wave picture of the quantum particle. We can modify this wave picture of the quantum particle to be like that. In all terms of the energy are expressed by the frequency like this. Consists of the rest frequency and then a totally frequency, and also we can use the dummy variable so that all the terms of the energy are looked as the frequency in the expression of the frequency. And then we can extract the Lorentz factor from this equation. Why I do this manner? You know that from the particle picture, we have now that the quantity which is transformed by the Lorentz transformation is the mass. And then Lorentz factor is the coefficient of the mass. And we don't yet know to the wave picture which one, the Planck constant or wave number or the frequency is transformed using the Lorentz transformation. So we don't yet know uh, in which one the Lorentz factor to be the coefficient of such a quantity. And from that modification, I just want to make that the Lorentz factor appears in the wave picture. Because as long as we know in the writing of the wave picture energy formula, Lorentz factors cannot appear explicitly. It is not like a particle of picture that the Lorentz factor can be appeared explicitly, so that we can get the understanding that between a particle picture and a wave picture are equivalent and can be easy in our making about the uncertainty formula. So in the uncertainty formula, we will have that the particle picture and the wave pictures are also equivalent because at the beginning of formula we have a mix the equivalence between a particle picture and the wave pictures with the extracting the Lorentz factor in the wave of pictures. So we can modify to this relation. And why I modify this relation for my second reason is we can by this via this way we can get the Lorentz factor in the term of the frequency. You know that in formally usually Lorentz factor is expressed by the velocity in the nominator and then the velocity of light in the denominator, but by this way, by this manner, we can express Lorentz factor in the term of the frequency. And then we can modify again this equation to be like that. In this equation, we explained all term of the energy in the term of the wave number after we have expressed all these terms by use the frequency. And now we express all the term of the energy of relativistic in the term of the wave number. So like the manner previously, we can also get the Lorentz factor in the term of the wave number. This is term of the wave number. And we can look both of the frequency and wave number, same condition, to express this Lorentz factor. Okay, in a previous procedure, we write all the term of the energy in the frequency like this. And the procedure is from this formula, we extract Lorentz factor to be like this, so that Lorentz factor appears, and from this formula we can get this formula. Okay, and equivalent with a previous procedure, we can also make this formula to be like this, all in the term of the wave number after we have written all the term of the energy in the term of the frequency. This is the a dummy variable omega star replace the k variable as we usually see in the ordinary formula. Okay, this is. And you can see also in the wave number there is k star. This is the dummy variable. This variable replaces the frequency as usually we see in the ordinary formula. Okay, and replacing from this form to be this form, we can also get directly to this form. And so the procedure in a previously and this procedure are equivalent. And then you know that via this modification we can make easier way to understand about the total energy and relativistic momentum in the wave picture than the particle picture. And for this equation we can write the total energy of the quantum particle is like this. So we can express this energy in the frequency, such as we express this energy in the quantum particle picture in the term of mass and velocity. And this is the first equation. And the second equation, we can also make the formula, rewrite the formula of the relativistic momentum in the language of the wave picture using the Lorentz vector which has modified. And then we have energy and momentum that energy and momentum is expressed by frequency and wave number.